Hello everyone, can you hear me? So today is the last Fourier transform lecture, and we'll break our chains from one-dimensional world to higher dimensions, and things are pretty straightforward. So 1D captures the essence of whatever we discussed about Fourier transforms. Extension to higher dimensions is easy, and in fact there is no reason to limit this discussion to 2D. Or it could be any D, 3, 4, whatever you want. But we'll, just to see how it extends from 1D to the higher D, we'll just stick to 2D today. And you could extend it to any dimension yourself if you wanted. And the significance of 2D in particular is just because relevant to, it's relevant to image processing, where images are two-dimensional objects. All right, so let's start with the continuous time Fourier transform. So now we have a signal of two variables, not just t, right? I would have normally used x and y because those are the good, the usual x and y dimensions in a two-dimensional plane. But since we use x for inputs and y for outputs in LTI systems, I'm going to refrain from doing that. So, and to be more consistent with our t variable, I'll just call them t1 and t2. They could be anything. They could be x and y directions of an image, right? So I have a signal that's a function of two variables, t1 and t2, okay? And I'm going to take the two-dimensional Fourier transform, which is going to be a function of two variables itself. These are the first and second frequency variables. Okay? And the definition is, now you need two integrals because you have two independent dimensions. And you multiply it with e to the negative j omega 1 t1 and e to the negative j omega 2 t2, integrate over t1 and t2, and both integrations go potentially from negative infinity to infinity. Okay? And there you go, you have the two-dimensional Fourier transform. Okay? Very similar to the 1D case, we just have two variables and therefore two integrations and two frequency variables. All right, so this is the analysis equation. Synthesis equation goes much the same way. So if I'm given the Fourier transform as a function of omega 1, omega 2, and if I want to recover the signal x, I do the inverse basically. Now you integrate big X, omega 1, omega 2, and what should I multiply it with before integrating? E to the j omega 1 t1, e to the j omega 2 t2, and I integrate over omega 1 and omega 2. And both go from negative infinity to infinity. Now, if you remember, in the synthesis equation for continuous time Fourier transforms, we had a factor of 1 over 2 pi, right? So we need to have that. And in fact, since we are doing two integrations, we need to do that twice. That means we take the square of 1 over 2 pi. Okay? So that's the continuous time case. Discrete time is very similar. dT/ft is defined similarly. ft. So I'm now given a signal of two variables, n1 and n2. But this is discrete, meaning that n1 and n2 are integers. Right? So what do? Multiply with omega 1 n1, e to negative j omega 2 n2, and instead of integration, I need to sum. I first sum over n1, the order doesn't matter of course, and then over n2. And the result is again a function of two variables, omega 1 and omega 2. These are two distinct frequency variables. One of those variables, omega 1, tells us about variation of the signal in the n1 direction, and omega 2 is a different frequency that tells about variation in the n2 direction. So to distinguish from the CTFT, I'm going to use this notation as we did in the one-dimensional case. Not that I can't write it as a function of omega 1 and omega 2. I just want to remind you that this came from a discrete time signal. When it comes from a discrete time signal, you have properties of the Fourier transform that don't belong to the continuous time case. For example, periodicity, right? So if you have e to the j omega 1 plus 2 pi, right? That's going to be the same as e to the j omega 1, right? And since this only depends on, e to the negative j omega 1 times n1, n1 is an integer, right? So you can immediately claim that you're going to be periodic in omega 1 with period 2 pi, right? And likewise for omega 2. So that's why writing explicitly e to the j omega 1 and e to the j omega 2 as arguments of the Fourier transform is useful, because you remember that this is a periodic object. So because of this, if I look at e to the j omega 1 plus 2 pi, e to the j omega 2, or if you wish, advance omega 2 by 2 pi, you'll get the same thing. Plus 2 pi, they're all the same things. So you have periodicity in both directions, both omega 1 direction and omega 2 direction, and they're equal to e to the j omega 1, e to the j omega 2. Okay? Identical property to 1D. Now periodicity exists in two directions. All right, do you have any questions? Do you agree it's pretty straightforward as an extension? Yes? That's right. So they are independent of each other. If you mix different omega 1, different omega 2, just think of, so you're basically changing bases, right? So you're trying to represent things in terms of these basis functions when you talk about DTFT, right? So just imagine what this would look like as a function of T1 and T2 for your choice of omega 1 and omega 2. If I pick omega 1 to be 0, that means it's going to be constant in the T1 direction. If I choose omega 2 to be 2 pi, that means it's going to be oscillatory in the T2 direction. But, every choice of omega 1 and omega 2 pairs is going to give you a different shape. Okay? So in the second part of this lecture, we'll actually look at some pictures, and it will give us a little more intuition about what these basis functions mean. All right. So similarly, we can define a synthesis equation for the DTFT, and that would be, I'll try to squeeze it here. If I want to recover my signal xn1 and 2 from the 2D DTFT, I will have to do an integration. Remember, DTFT is a funny thing. It's a hybrid. It takes in discrete signals but returns a continuous function of the frequency, right? And DFT makes them even, makes both of them discrete time. But anyway, so we'll talk about DFT later. So to get the signal back, again, you multiply by 2 pi squared, divide by 2 pi squared, and then do a double integral. Integral because we're integrating over the Fourier transform, which is continuous. 2. And we need to multiply with e to the j omega 1 and 1, e to the j omega 2, and 2, d omega 1, d omega 2. All right. So similar questions arise as to whether or not these integrals converge. In the Fourier transforms, both continuous time and discrete time, we talked about a sufficient condition which was absolute integrability of the signal that guaranteed the existence of these integrals. But then we saw that these are actually not necessary, sufficient, maybe a little conservative. For example, the sinc function, which we know has a well-defined Fourier transform, a box, right, a rectangular pulse, that itself was not integrable. Nevertheless, the integral converges, right? So the integrability is only a sufficient condition. And then we relaxed Fourier transforms, in fact, further to allow for situations where that integral doesn't even converge. And the way to go was to deal with these delta functions in the frequency domain through the theory of distributions, which we did not get too much into. So, so the absolute integrability or summability, if you're talking about discrete time signals, will guarantee convergence of the Fourier transform. So whatever integral or summation we use in the definition, the absolute integrability, summability conditions assure us that those things are well defined. Those integral summations will converge. So what they mean is, if I have a continuous time signal of two variables, absolute integrability means when I take the absolute value of that and integrate over T1, T2, that is going to converge. Likewise, summability means if I have a discrete signal, function of n1 and n2, and if I sum over n1 and n2, both from negative infinity to infinity, that sum also exists. Like in the 1D case, you can relax those, but we're not going to go into that now. All right, here's a simple example. So discrete time signals, we use these stem plots. Remember, you put the value, draw a stem. But how do I do this if this is a 2D signal? For example, what if I'm talking about the so-called delta function as a function of two variables? So let's see what the Fourier transform is, what the DTFT is, of this signal, which is simply delta. That means it is 0 everywhere in the n1 and n2 space, except when both are equal to 0. Okay, so for all of these, in both directions, I'm going to put a 0. So now imagine, so when it was a 1D thing, we were looking at it from the side, right? N versus x of n, right? But now it's a function of both n1 and n2, so just imagine looking at it from the top. Okay? So when I look at the top, I'm seeing a bunch of zeros, right, for all values, except at n1 equal to 0 and n2 equal to 0, there's a spike coming out of the plane with value equal to 1. And elsewhere, the value of the signal is 0, okay? So that's the natural delta you would define in the 2D, okay? So if I take the Fourier transform of that, what would I get? It's a double sum over n1 and n2. Again, order, of course, doesn't matter. Delta times these guys. But the good news is that this delta is 0, except for one particular pair, n1 and n2, which is when both n1 is 0 and n2 is 0, right? So what will come out? So that really is the value of what I'm summing at n1 equal to 0 and n2 equal to 0. n1 e to negative j omega 2 n2, when n1 and n2 are both zeros, therefore I get just 1. So the DTFT of the delta is fixed. It's 1. It doesn't even change with the frequencies omega 1 and omega 2. It's just flat, which is a natural extension of the 1D case where we had a delta function and its Fourier transform was equal to 1. Right? Now it's a two-dimensional function. It's a function of two variables, rather, omega 1, omega 2, but it doesn't depend on either. It's always 1. Make sense? Okay? So really there was no summation in this case because delta is so simple. So if I ask you to write this delta in terms of the delta of n1 and delta of n2, the one-dimensional signals, can you figure out a way to do so? Can I say delta is equal to something of delta of n1, some operation delta of n2? Would you add, subtract, multiply, divide? If you multiply, that will do, right? Because it will vanish unless both n1 is 0 and n2 is 0. Make sense? So that's just a simple way of writing delta. You know, if I didn't want to draw this picture, if I want to define it algebraically, the two-dimensional delta, that's how I would have written it. Similarly, you can, if you want to define a two-dimensional step function, you can write it as u of n1 times u of n2, and that simply means that your signal in the 2D space will be ones when both n1 and n2 are non-negative, and elsewhere the values will be 0. Because I'm multiplying, if either n1 or n2 is negative value, that will kill the whole thing. Okay? So it's like an AND operation, if you will, right? Because you're multiplying. All right. So anyway, that was an aside. That's not quite related to this example. All right. So let's look at another example. And that is a two-dimensional signal that looks like this. X of n1 and 2 equal to some number a raised to power n1, another number b raised to power n2, and we kill the signal when either n1 or n2 is negative. Okay, that means we multiply it with the unit step, the two-dimensional unit step. All right, so we want to know what the Fourier transform of this is. So the Fourier transform, you'll remember, is the double sum. So, but remember first that I can write this as the product of u of n1 and u of n2, right? So really this whole signal, this two-dimensional signal, can be separated into a product of a function of n1 alone and the function of n2 alone, and those functions are, of course, a to the n1 un1 times b to the n2 u n2, right? So it's a product of two independent functions. One is a function of n1, the other is a function of n2. So then the double sum we have actually can also be separated. So I'm summing, remember, actually from 0, because the signal takes 0 values when n1 is negative, to infinity, and n2, 0 to infinity, of a to the n1 and b to the n1. N2 rather, b to the n2, right? And because one only depends on n1, the other only depends on n2, we can split this sum into a product, n1 e to the negative j omega 2 n2. So I can write this as the product of this sum, a to the n1 e to the negative j omega 1 n1, times the sum, this time over n2, to n2, right? So what do you know about this? This is our good old example for 1D Fourier transforms. Let's see who can remember. 1 over 1 minus a. Okay. But you forgot to say when this is true. If a in absolute value is smaller than 1. Okay. And this guy similarly is 1 over 1 minus b e to the negative j omega 2 if b is less than 1. Okay? So a being less than 1 and b being less than 1, they are basically the absolute integrability condition, right? So under that condition, we get the Fourier transform to be the product of these two terms. And we benefited greatly from the fact that our signal x could actually be written as a function of n1 multiplying a function of n2. So we call this the separability property, meaning that although our function pretends to be a function of two variables, it actually is a product of two independent functions. I mean, it is a function of two variables, but it has a very specific form. So that is the so-called separability property of the 2D, either CTFT or DTFT, doesn't matter. But I'm going to write it as a property of DTFT, but keep in mind the same thing is true for CTFT as well, of DTFT. Okay? So if our function of n1 and n2 can be written as a function of n1 alone times a function of n2 alone, then the 2D Fourier transform is simply the product itself of the two signals, the two Fourier transforms in 1D. Okay? The reason is very simple. Essentially what we did in the example is the proof, right? In the example we were able to separate the signal as a function of two things, and then we split the double sum as a product of individual sums. So same thing works if x has this separable form. And then you have two separate summations. One gives you this, and the second gives you that. So it's as simple as that, right? So that's a special case, but an important special case. So separable functions are easy to deal with. You essentially take individual 1D Fourier transforms and multiply the Fourier transforms. As simple as that. Does it make sense? Okay, so I'm not going to write a separate proof. The example was the proof, essentially. You can just change this to x of n1, x of n2, instead of this and that, right? So make this x of n1, make this x1 rather, x1 of n1, x2 of n1, make this x2 of n2, and there you go, all right? Okay, so separability makes life easier if you're dealing with multidimensional Fourier transforms. Again, there's no reason to even restrict it to this to do 2D. It could be 3D. If I have a three-dimensional signal, I mean function of three variables, if I can write this as a product of three functions of independent variables, then the same thing is true in 3D as well. All right, so now that we understand two-dimensional signals and their Fourier transforms, we can talk about two-dimensional systems as well. And those are actually important. Whenever you do Photoshop or anything like that, you're actually doing a two-dimensional system application. The input being the original picture you've taken, and the output being the modified picture that you've modified, right? So I'll call these 2D systems. And so now the input is a two-dimensional signal, and you have a system that modifies it and spits out an output, which again is a two-dimensional thing. Okay? Maybe the input is one image, the output is another image. Okay? If I apply delta, the unit impulse as my input, the output, we'll give it a special name. We'll call it h of n1 and n2, and we'll call it the impulse response. Now, the impulse response itself is a two-dimensional, I mean, it's a function of two variables. I shouldn't say two-dimensional. It's a one-dimensional signal itself, but it's a function of two variables. Okay, it's basically a surface in the n1 and 2 dimensions. All right? Let's think of an example. Maybe one of our examples in the 1D case was the so-called moving average filter. So we could, in fact, come up with a 2D moving average filter. So if your image is noisy, so maybe you scanned an old photo or something and it's really grainy, right? You may want to smooth out that graininess by using an average filter. So the way it works is you'll have a certain window length in both dimensions. For the sake of simplicity, let's assume that the length of the window in each direction is 3. So what I'm going to do is, so I have x and 1 and 2 coming out of the plane. That's a convenient way to visualize two-dimensional signals, right? And 2. So for each integer combination of n1 and n2, there is a sort of a stem sticking out of the page. I can't see its values because I can't draw it in 3D. But, you know, that's a natural extension of the stem plots we did for the 1D case. So imagine something sticking out at each of these points, right? So that's our two-dimensional signal. So what we do when we're averaging is, let's say that I am at point, I don't know, 2 and 2. So I'm at this particular point, right? What I'm going to do is I'm going to replace the pixel value here at that point with an average over all of its neighbors. And if the lengths in each direction are 3, as I said, I would take as an example, then I have 9 sample points. That particular point, as well as its, how many neighbors does it have? 8? 8 neighbors. So I'm going to add them up, divide by 9. So if there were unnecessary fluctuations because of the grainy original image, those will be filtered out. It will be smoother, right? So how can I express this operation? Well, I can say that the output at a given point n1 and 2, which I marked with a star here, is going to be a sum of x of n1 minus k1 and n2 minus k2. And I'll let k1 and k2 move between negative 1 and positive 1. Okay, each one is allowed to be negative 1, 0, or 1. So we have 3 by 3, 9 possible combinations for k1, right? So therefore, I'm going to do a sum. k2, negative 1 to 1. And of course, I need to divide this by 9 so that I really averaged. Okay, I hope you can read this. So that's what the moving average filter is doing, right? So it looks at each point, looks at the neighbors, averages the values, thereby smoothing out, you know, fluctuations, rapid changes between the data points. Okay, so you can think of this as a sliding window. You slide it around the image, and every point gets assigned the average of its neighbors. So you all see that this is going to smooth out the image? Is it clear? Yes? Okay. All right. Now let me ask you, what is the impulse response? In other words, if the underlying image is just a spike at n1 equal to 0 and n2 equal to 0 and 0 elsewhere, when I do this averaging, what do I get? You'll get a bunch of 1/9s, but where? Here, here, here. All these 9 values around 0, you'll get 1/9s. And all other points, at every other point outside of this interval, this window here no longer includes the origin. And the origin is the only place where there's a value that's non-zero, so you're going to get 0 elsewhere. So all others are simply equal to zeros. Okay? So that's our h of n1 and 2. Okay? Or I could just say that's equal to 1 over 9 if n1 and n2 is less than or equal to 1, 0 otherwise. But the picture is easier to look at. Okay, so what would be an analog of an LTI system then? In 2D, you can extend the same notion, still linear. If I give the system two different inputs, x1, one image, and x2, another image, and if I add them up and give it to the system, what it spits out is the sum of the individual outputs. Right? Same idea. Now, time invariance is the same thing as well, but the word time comes from our thinking of in the 1D. Somehow, traditional discourse was, I think, dealing with one-dimensional functions of time, audio, things like that. But no reason to really separate this from the 2D case where you do image processing. So in 2D, you can again define time invariance, but it's a little funny to call it time invariance. It's basically an invariance to the two variables, whatever they are, right? So a more precise word, in fact, is shift invariance rather than time invariance, because even in 1D, who tells you that variable is time? It could be anything else, right? So we are really shift invariant, and if we call it shift invariant, that works in any dimension without having to attach a meaning to the variables. Okay? So we can then think about linear shift invariant systems. In the usual way. So if I give the signal n1 and 2 to my system, and what comes out is y of n1 and 2, and if I give it a shifted signal, perhaps by k1 in the n1 direction and k2 in the n2 direction, the system will spit out the same output, again shifted by the same amount in each direction. All right? So as you may remember from our 1D discussions, an important property of LTI systems was the convolution property, where if we knew the impulse response, we could find the response to any other input through a convolution integral. So something like that works here as well. Let me first ask you, how many of you remember how we derived that? The convolution problem. One person does, two. Okay. The others might, with some nudging, I guess, remember. All right. So here was the idea. And it's very simple. It's good to review this because that's so fundamental. It's like one of the most important things covered in the first half of this course, which we are wrapping up today. So we took our signal x of n. That was a function of the discrete variable. And what we said was, I can just write this as, x0 times delta of n, which is this guy, right? Plus x1 of delta of n minus 1, which is this value, right? And plus all the others. Does that make sense? So each of these things here are a function of n, but they are non-zero only at a given value because of the delta involved in them. And then we said, well, since this is an LTI system, the output, if the response of the LTI system to delta is h, then the output to x0 times delta will be x0 times h, right? x0 is just the scaling factor in this case, right? In addition, because we have a sum,
we'll get x1 as another scaling factor, and the response to delta n minus 1 because of time invariance or shift invariance will be h of n minus 1, and so on, right? And, if I patiently write this out and turn it into a summation, this really is the definition of convolution. Yes? Makes sense? So there is no reason I can't do the same thing for a two-dimensional signal. If I have x of n1 and 2, I can write that as x of 0, 0 times delta of n1 and 2 plus x of 0, 1 delta of n1 and 2 minus 1, and so on and so forth, right? So in general, I can add, if I include every term, that's going to look like a double sum of x, some dummy, call it k, I guess we use it k, k1, k2, delta of n1 minus k1 and 2 minus k2. Okay, so here we split the signal into a sum of many signals, but each of these signals are very special. They have a single delta in them, so they are 0 everywhere except at the point of interest, which is defined by k1, k2, right? So sum over k1, sum over k2, right? So from the LSI properties, linear shift invariance properties, I have the following. I know that the response to delta of n1 and 2 is h of n1 and 2. And if it's shifted, then the response by the shift invariance should be h of n1 minus k1 and 2 minus k2. So therefore, the response to the double sum of x of k1, k2, delta of n1 minus k1 and 2 minus k2 will be, again, a double sum. And these guys are just coefficients that are inherited. k1, k2, h of n1 minus k1 and 2 minus k2. All right? So this summation goes over k. K is our dummy. Minus infinity to infinity, k2, negative infinity to infinity. Right? So that would be the output. So y of n. So if I apply the input, x of n1 and 2, to a linear shift invariant system, the output is going to have this form. And that is nothing but a two-dimensional convolution. Right? It's just a one-dimensional convolution definition naturally extended to 2D with a double summation. Yes? Yeah. Yeah, so you keep one the same. In this case, x stays as it is. Only it becomes a function of the dummy variables x, k1, k2. So x is a function of k1, k2 stays as it is. It's a surface in the two-dimensional plane, right? And then we have h. We flip h in both directions. You turn it, with respect to k1, you flip it. With respect to k2, you also flip it. And then you drag it by n1 in one direction and n2 in the other direction. And then multiply them, sum over the whole area. That's basically the graphical convolution, but it's a little harder to visualize as we increase the dimension. All right? Okay, so that's the definition of convolution. And of course, all the properties we've seen about convolution are true in this case too. For example, I could just apply this to the flip and drag to x and leave h alone instead. And I would have gotten the same exact result. Oh, h of k1, k2. So that sum is no different than this one. Just the same property we had in the 1D case. All right, so with convolution, I'm not going to dwell too much on these things because really they are identical to the results we had in the 1D case. So the convolution property of the Fourier transform is still there. Again, I'm going to state it for DTFT, but keep in mind it's the same in CTFT as well. So if I take a convolution of two things of two signals, two-dimensional signals, and 1 and 2, what's happening in the 2D DTFT domain is, guess what? I am multiplying their 2D Fourier transforms. So h of e to the j omega 1, e to the j omega 2, x of e to the j omega 1, e to the j omega 2. There's a course here, I think it's a CS course, so it's called Computational Photography. Has anybody taken it? If it still exists, I mean, it probably does. I don't know how often it's given. But I really recommend it. It's really cool. It's like Photoshop. But everything is like this. You know, when you're taking an image and when you're sharpening it or smoothing it or all these Photoshop types of things, you're really doing convolutions with an appropriate kernel, with an appropriate impulse response. Okay? We saw an example of smoothing with the moving average filter. Things like sharpening or edge detection and things like that are very similar. They go in the other direction where you emphasize the differences, right? So, and it gives you a lot of intuition about, you know, what's really happening, what convolution is really doing in 2D, and it will reinforce your understanding in 1D as well. All right, so that's that. And by the same logic, we could say that you know, the impulse, I mean the response of an LSI system can be captured by the impulse response of the LSI system, which would be the Fourier transform of its impulse response times the Fourier transform of the input. You multiply them, you get the Fourier transform of the output, right? So convolutionary things in the, not time, in this case the regular domain, become in the frequency domain simple multiplications. All right, so then I could ask you, you know, the analogs, about the analogs of everything we did in 1D. For example, we talked about filters, right? What is an ideal low-pass filter in discrete time? It is a filter where the frequency response, I'm now talking about 1D, just to remind you, is 1 below a cutoff frequency. And of course, because we're in discrete time, Fourier transforms have to be periodic, so you would see a copy of this centered at 2 pi. Okay? So then you would ask, you know, what is the impulse response from which you would get this Fourier transform? And we know the answer to that, of course. It's a sinky function. It's not exactly sinc because of the periodicity in the Fourier transform. It's a sign by sign. It's a periodic sinc, essentially. It's not the standard definition of sine pi x by pi x, but it's rather sine pi x by sine is something much slowly varying x, okay? Just so that you get, because of the periodicity of the Fourier transform. So you could ask the same question, right? So suppose I want to design an ideal low-pass filter to, you know, filter my photographs and make them look smoother, right? What would be the kernel? What would be the impulse response with which I'm taking the convolution, right? So you can ask the same question. Then the question will be, what is the, first of all, the first question would be, what is the ideal low-pass filter in the frequency domain? Now we have a frequency domain with two frequency variables, omega 1 and omega 2, right? So can you, what would be the analog of this rectangular thing in 1D? Actually, now you have some options, right? But tell me any one. I mean, you can do it in more than one way, but what would be one way of doing this? A square, right? And in fact, you don't even need to have the same cutoff. You can have a cutoff omega c1 in one direction and omega c2 in the other direction. But if you want, so then you're saying here it's 1 inside the box, and outside it's 0, right? But then remember, this guy has to be symmetric, right? I'm sorry, periodic in both directions with period 2 pi. So you would have the same thing repeated at 2 pi and 2 pi away here also, right? So it would be a shape like this. This would be the desired frequency response, right? So then I could ask you, what is the impulse response that you want from your 2D filter to give you that frequency response? It'll be a 2D thing, but can you tell me? So, okay, this is the picture that I was drawing on the board for those of you watching. Okay, so this is the frequency response I want. That's an ideal low-pass filter in 2 dimensions. It will cut off frequencies in the omega 1 direction beyond omega C1 and in the omega 2 direction beyond omega C2. Potentially different cutoffs in 2 directions. So, any ideas? How would I go about doing the inverse Fourier transform of this so I know the impulse response that I'm looking for? I can apply the definition. I can do that double integral thing, you know, the synthesis equation, right? But maybe there's a simplification because of this particular shape. Remember, we did some examples of 2D Fourier transform half an hour ago, and the trick was they were separable, right? When H is separable, it can be written as H of n1 times H of n2. The Fourier transform can be separated as well. Likewise, we can go backwards with this. So if you can tell me that this Fourier transform is a product of 2 independent Fourier transforms of omega 1 and omega 2, I can use that to go back and multiply one-dimensional inverse Fourier transforms. So, what do you say? Yeah, so this is a product of 2 rectangles. One is a function of omega 1 that ends at omega C1, right? The other is a rectangle with bandwidth omega C2 in the omega 2 direction. If I multiply them, I'll exactly get this shape, right? And therefore, the impulse response will be the product of the impulse responses for those 2 one-dimensional things. So that's basically separability at work. So basically using the facts that we already know. So I can write this as a product, H1, H2, and then the impulse response is a product of H of n1, H2 of n2. And these are the sync. Is that even right? Yeah, I think it's right. What's confusing me? Okay, I think I said some. Do you believe what I just said? So this sync is correct, right? Okay, so, okay, now I know what I was confusing it with. So I said something that wasn't entirely correct 5 minutes ago. The inverse Fourier transform of this is a perfect sync. Nothing wrong with that. So what I confused this with was if I take a pulse in the time domain, take the Fourier transform, that should look like a sync, but it's not an exact sync, it's a periodic sync, right? That's what I was thinking about. But for this, it's a perfect sync. Yes? Agree? Okay. So, yeah, now you have the product of 2 syncs, and you may want to see what that looks like as a function of n1 and 2, and of course, it's a 2-dimensional thing. You know, Python, MATLAB, all these things will give you cool commands to plot things in 2D. In MATLAB, it's surf. There's a new homework coming up where I asked you to do something like this, and I gave the commands in Python. I don't remember off the top of my head. So that's what it looks like. It's the product of 2 sinks. One is the sink of n1. The other is the sink function of n2. And you multiply them, you'll get this 2-dimensional surface that looks like this. Right? Still looks like an octopus, but right? Makes sense? So taking the convolution with this, so imagine having an image. Pixels have values, maybe grayscale values, right? So taking a convolution with something like this is going to smooth out the filter. It's a more sophisticated way of filtering than the moving average filter that I just described. Because if you look at the moving average filter, its frequency response is not as sharply defined as what we have in this picture
right? Okay. Questions? Now, this is not the only two-dimensional low-pass filter you can define, though. Why should it be these rectangular regions? Why can't it be this? Right? It could even be an ellipsoid. Maybe again, if you want to differentiate between frequencies in the two directions, maybe you want to be more permissive about variations in one dimension and less permissive. So then you may want different cutoffs, right? But you can just tweak this into an ellipsoid. So that will do. You don't necessarily need a rectangle, right? So then the question is, what kind of impulse response will give me that frequency response? Oh, the colors. So the one at the center is a little more solid. I think I did that intentionally back when I was doing this. The others look more pale. There's no reason. I just want to emphasize that the others are basically copies of the same thing, right? I mean, they have the same values and the same everything. All right. So is this a separable function of omega 1, omega 2? Can I write it as some function of omega 1 times another function of omega 2? Doesn't look like it, right? I mean, these rectangular shapes work perfectly, but now you have these circles, and it's not clear how you would write those. So the value is 1 inside the circle, 0 outside, right? It's not clear how you would define a function so that the product of two independent functions give you that, right? It's not separable. So, and because of that, you can't get away with this trick of using 1D Fourier transforms, multiplying them. You have to actually deal with that two-dimensional, two double integration to go back and find h of n1 and 2. Okay? Some patient people did that. Wasn't me. So this is the expression. If I restrict myself to the box between negative pi to pi and negative pi to pi in both dimensions, and everything else is a copy of that box, right? So then the function can be written in this form, okay, which is straightforward. And if you insist on doing the double integrator to get the impulse response h of n1 and 2, the inverse Fourier transform, this is what you find. Okay, so that is not itself separable, obviously. And then it depends on this weird function J1, which is called a Bessel function of the first kind and first order. If you want to know what that is, I'm not the person to ask. You have to go to wolfram.com and look up Bessel functions. Okay? So that's what I would do if you ask me. So I'll just refer to the website. Okay? So, there's a way to derive this, but it's not straightforward at all. And let's look at what it looks like. Looks cool, right? Looks like you've dropped something in the water. Now, actually, the Fourier transform we were looking at the top has circular symmetry, right? Because it's circular, if you rotate it, it still looks the same. And the impulse response inherits that property, so it's also circularly symmetric. If you spin it around about the center, it's the same shape, which is just an aside. All right? Okay, any questions? All right, let's take a 5-minute break. Look at the pretty pictures in the meantime, and then we'll continue from here.